So good afternoon, everyone. So today we have opportunity to have an eminent personality from Boeing, Mr. Arvind Kumar Pandey. He will give you a brief lecture about the emerging strengths in aviation industry. So we welcome Mr. Arvind Kumar Pandey, who is live from USA. So it's hand over to you, Mr. Pandey.
Thank you, Dr. Bridges, and many thankful to all the students who have joined here, and thankful to university who has given me opportunity to provide the guest lecture. Good afternoon, everyone. So, are you guys ready? Yeah, I think everyone is silent. And today I'm going to talk about the topic advanced and emerging technologies used in the aerospace. I will share my screen. Please confirm when my screen is visible.
You can go to full view.
Yeah, just now I changed to full view. Let me reshare if it is not the full view. Is it full view now?
No.
Okay. So what you see on my screen, just help me to know so that I will correct it quickly.
There is
Any
an air.
presentation?
Yeah, there is an presentation skill arrow upwards, and then you can share your full screen or
Yeah. Okay. Entire screen. I'm sharing my entire screen
yeah.
at this moment.
Then go to the PowerPoint in the screen. Go to the
Yeah.
yeah. Then make a slideshow.
Yeah.
Then you will make a full
I made
screen.
the slideshow. Is it full slide visible?
Already fixed the his
It's part to be make it small.
maybe I
Yeah. Just wait. We will do it. Hmm? Minimize it.
I only can that in big
Hmm?
that big.
I think you can start. It's
Okay.
more visible.
Yeah. So uh, Dr. Bridges has given a brief introduction. I will just add more few lines regarding my experience. I'm having 15 years of experience in the aerospace industry. I am graduate and postgraduate in the aeronautical engineering, and I'm also pursuing my master in business administration for the operation management. I have worked in aviation industry on the preliminary design phase. So those who are not aware, preliminary design phase where from the scratch on the paper we start designing the aeroplane, we start working on that, we bring it to conceptual phase, and from there we build the product. So I have seen all those life cycle. I have also seen the life cycle in the aerospace industry, where we operation in operational area, where we uh, deliver to the product to the customer, and then we deal the all the service issues which comes with this background. I will be happy to interact with you everyone all, and this will be a interacting session where with the 15 years of learning, every day I'm learning. So feel free to ask any question, and no question is small or big. Every question is valid here. So feel free to ask the questions. Same time, through your questions I will also be learning. So it's a both the way. So before starting to the emerging technology, uh, I will just talk about what are the content I'm going to cover in this session. I'll be talking some of the content, sustainable air fuel. I'll be talking about electric airplanes. I'll be talking on thermoplastic. I'll be also talk on some MQ-25. This is a Boeing product. Boeing has built this aeroplane, collaborative combat aircraft. I will also talk some of the Jetopetra, fluidic propulsion systems. I will talk Clean 3 technology, and I will also talk on bypass turbo fuel engine. So my first question will be, how many of you well aware that what we have decided in the Paris conference? Paris, there is a conference happen to save the environment, and what is the key outcome of that? How many of you aware? So in that conference, basically all the world leaders met and decided that under international treaty, to reduce the global warming will reduce by 2 degrees centigrade. This is a big challenge. We cannot do that immediately. And that drives the, the innovation and advancement in the aerospace industry. I'm presenting one graph. I will just show that zoom view further of this graph, because this is the key of all the innovation which is happening currently in the aerospace industry. So let's see, this graph is developed over the years on the horizontal axis, and the vertical axis, the CO2, carbon dioxide emission in metric ton. And if we see the trend from 2000 to 2019, almost 200,000 metric ton CO2 emission we are doing every year on an average. But after 2019, there is a curve deep gone down. The reason behind is that Corona has came, and for that reason, airline was not operation. If you see in this curve, a very interesting fact is, when the curve start from here, 2023, we are almost 2023 in, almost we are able to gain back that aviation industry same at the level at 2019. And if we are not doing any new innovation in aerospace industry, we are not bringing any new product, then how much CO2 emission we will be doing? The red graph shows the trend that over the 2050, if we do not advance our technology, if we do not innovate, then the almost carbon dioxide emission will be making double by 2050. So how to bring this down? Everyone is thinking we have to protect our ozone layer. We have to save our humanity by protecting the ozone layer. How can we do that? We have to stop generating CO2. And how can we stop CO2? Because aviation industry is heavily generating CO2 because of their engine. They are flying, engine is running, they are burning the fuel, and CO2 is coming into the atmosphere. The best thing, either we can replace the fuel which reduce the CO2, or we can change the technology. Current industry is working on the both the way. They are also working to develop new fuel, adopt new fuel, adopt new technology, and change the design of the aircraft. When we think about the aircraft, we if we close our eyes and just imagine what is the aircraft, only two concept comes in general, either fighter or the passenger. Passenger aircraft also has a very conventional shape, a cylindrical body, two wings, landing gear, tires, and the fighter aircraft has very stealth kind of a structure, a pilot seat, very high velocity. See the graph here. We have to reduce this, the CO2 emission. And how can we do that? SAF update means sustainable air fuel. If we use the sustainable air fuel, then we can reduce this. See the green curve, which says the 50% of emission reduction we can achieve by 2050 just by using the sustainable air fuel. Same time, if we bring the operational improvement, we can further reduce some of the CO2 emission. If we use new aircraft diffusion trajectory, then also we can reduce. If we can airline fleet renewal, what is basically the airline fleet renewal? This term is related to in the industry already existing aircraft. We are replacing the parts. Old part we are replacing with the new advanced technology part. Aircraft is old. The parts we are replacing as a new. So we are upgrading our old aircraft. Same time, we are bringing the new aircraft technology. So those technology can be electric. This requirement is driving our innovation. That if we are thinking for the electric engines, the reason behind that change or innovation is the same. If we are thinking to use more sustainable air fuel, reason behind that reason behind that is same. If we are thinking to build a optimized aircraft or eVTOL, the reason is same. Everyone want to reduce the CO2 emission. This we have thought, the aerospace industry engineers has thought 2010, and over the period till 2023, 13 years, whatever the technology innovation we did 10 years back, that technology got matured, we are implementing now, and we'll be keep doing that. Coming 25 years, we have already dreamed the vision, what we have to do, what we have to achieve in the aerospace industry. So when a new student, new engineer is coming in the aerospace industry, basically roadmap for him already we have developed. He will not be doing anything new in his era. He will be only doing what the roadmap we have developed for him. But now the upcoming student has to develop what after 50 years students will be doing. They have to think in that direction. Very key important point I will be sharing from here. There is a term called net zero carbon emission by 2050. In October 2021, in 77th IATA ASEAN in Boston City, IATA approved that industry has to achieve a net carbon zero emission by 2050. And this commitment is well aligned with the Paris Agreement goal for limiting the global warming well below 2 degrees centigrade. So just 65%, a potential scenario is that 65% of this will be abated through sustainable air fuel only. So what is this sustainable air fuel? This is a biojet fuel. All the airline company is adopting. In October 22, a long-term aspirational goal to achieve a net zero CO2 emission by 2050 at the 41st ICOA assembly has been decided. And what we have done so far, SAF production tripled to 300 million liters from 100 million liters in 2021. So this shows the demand of the sustainable air fuel, demand of changing the technology. Within a 1 year, we have adopted many new technology. We have changed many old parts with the new technology parts. We have changed our fuel, and within 1 year, we have achieved this much. Let's talk about my next slide, which is electric aeroplane. So we understand the background. The background is we have to reduce the carbon emission. To reduce carbon emission, we have to adopt new technology, and we have to change our designs. The first impact has happened. All the aerospace company, engine manufacturer company, GE, Rolls Royce, Pratt and Whitney, they got affected because of this decision. Their idea was we have built a good engine which is good in demand, and we have to generate the revenue. They said we have spent almost 20 to 20 years to develop a new engine which can be used at a faster rate. We can drive aircraft at a faster speed, and we want to sell that. We want to earn the money, but due to Paris Agreement to reduce 2 degrees centigrade carbon, everyone is saying now we cannot sell our aircraft engines. Then global committee had decided, okay, we will give you some relax. The relax is maybe 10 years. For the 10 years, you can use your or old aero engines. You can sell in the market, but make sure you are doing some changes in those engines, which will reduce carbon dioxide. Same time, we will fund. So there is a committee under NASA is formed, which has funded to Rolls Royce. They have funded to Pratt and Whitney. They have funded to all other aero engine manufacturing company, and they said we will be funding you to develop a new technology through which in future you deliver a engine which reduces almost 10% CO2 emissions. Lot of many startup companies also got that money. They are heavily investing in the electrical aeroplane. This is I'm showing a Cessna aircraft. 2021 this flight has happened, but there is some limitation if we build a heavy battery and we run the engine, because the battery technology has also not emerged so well that it can propel a engine which can drive a wide body. So I will come back on this wide body. What is wide body and what is narrow body? Most of you will be aware because then day to day life you'll be reading those. A350 aircraft, A380 aircraft, these are called wide body, where more passengers can sit and twin aisle system works. Now, A320 aircraft, A737 aircraft, these are single aisle system. So these are narrow body. Current battery technology has capability to generate the power for narrow body aircraft, but it does not has capability to generate the power of twin aisle or wide body aircraft. So what is the industry requirement? So industry requirement is very clear. I need a new technology in the battery which can generate more power. And battery technology, lot of companies are investing money to come up with uh, a robust model, robust designed, robust energy saving method which can help this aerospace industry. So success is yet to receive in that direction. What will happen if we say we will leave away this wide body? We are good with narrow body. The problem with the narrow body is it it has to go only for the short distance flight. And if we the major aviation industry fuel goes to start in the engine, takeoff, and the landing. I can replace all the aircraft with the battery, and I will only use a narrow body. I will not use a wide body. The industry problem will happen. Narrow body flight will be for a smaller duration, maybe 1 hour. A long flight, more than 6 hours, 7 hours, we cannot continue. In between, every time we have to come back to some airport, we have to recharge the battery. So this is not a sustainable solution. The current industry engineers has to think how can we solve this industry problem? What new I can bring in the battery technology and the engine technology which can help aircraft to run for a longer duration. If we run the aircraft longer duration, we do not have to do much takeoff and landing. We do not have to refuel our aircraft. So if we are not refueling much, we are not doing much landing and takeoff, we are not burning much fuel. It's simple. When aircraft is in the cruise or in the, you can say it is when it is in the mid-air, very less fuel it burns. When it is taking off and landing, almost 3 times or 4 times fuel it burns. That's the difference. And this difference we have to solve. Let's move to the next technology. So first we understand the context, what is the industry need. We also understand there is a immediate solution, but it is not going to help us. Very first slide we have seen that technology drive is going towards not only the engine side, it is also going to change the design, shape, and the material. Initially, all the airplanes were metallic body, titanium, and the aluminum we were using. The next phase, we started using the composite. And in the composite also, mostly the carbon fiber. And the carbon fiber composite also, if I can say, is thermosetting plastic. In the thermosetting plastic, what is happening? It is a cheaper, means easy to build aircraft. Technology, when the composite technology came, aircraft industry was took it hand to hand, and it was reducing weight for all the aircraft. When we reduce the weight, definitely we save the fuel. But it creates another problem. Though it is helpful in weight saving, but it is creating a scrap, lot of scrap. Once the thermosetting plastic, carbon fiber, we have built an aeroplane. Our problem is what to do with the scrap. Over 30 years, when the aircraft I'm going to dump somewhere, the aircraft will retire. How will I utilize that material? It is not easy to reuse that material. When we are not reusing, we are creating a scrap. And that scrap will not mix with the soil easily. So what is the alternate solution of that? The alternate solution of this problem is they have brought a thermoplastic composite. Thermoplastic composite has some advantage over thermosetting plastic. The major advantage is we can recycle it. We can reuse this. So same as composite, it gives very high strength to weight ratio. It is heat resistance. It is very flexible. Cost is trade-off. So when I say the cost is trade-off means initial days when we use thermoplastic, it will be costlier compared to metallic aircraft and composite thermosetting composite aircraft. But over the period, suppose I have built initial five aircraft I'm building, so it will be very costly. After 200 aircraft, when I have manufactures, this will be cheaper. And over the coming 2 years, 3 years, same time, the thermoplastic technology and the manufacturing capability in the industry will also be upgrading. And if I keep upgrading myself over the 5 period time, then I will see after fifth year and with more demand, this technology will become cheaper. Current industry, if I see the Collins Aerospace, they are preparing the thermoplastic nacelles. If I see the Airbus, they are preparing some of the fuselage section with the thermoplastic. Even they are thinking to build this pressure bulkhead, the tubular structure end towards the cockpit and towards the end. There is a to close the pressure vessel, to create a pressure vessel. There will be a closed lid that is called as a pressure vessel after bulkhead design. So that they are trying to build. So what happens when they will build it? Because when will um, one more important point I will tell you, the industry challenge. I have gone and seen this factory, aircraft factory, and that oven in which they do. So what they do, they do hand layup or automated fiber placement. They do. They will lay up the shape. Once the shape of the structure, for example, I have to shape this arc. In aerospace industry, it is double arc. Both the side arc will happen in the fuselage or the wing. It is not only one sided arc feature, it is two sided arc feature. So fuselage will be having many places double arc. In that, when I will do layup, and if I go, there will be a I can say for that A350 size of fuselage, A350 size of nacelle, A350 aircraft, or I will say 777 aircraft. What is that nacelle size? It is three multi-story. That much size oven I need. And when I will prepare my nacelle, I will keep inside that, in that oven. And it requires 24 to 36 hours lean time. So once composite I have do it hand layup, for curing, I will keep it in the oven. So those 36 hours, and this creating oven is very costly, very, very costly. No one can buy like the way they want. Even the aircraft industry also cannot create and keep oven multiple like 10 or 20. They cannot do. It's a very, very costly. If they create one or two oven or 10 means 5, that's enough. That itself is a very huge cost in that, because if we keep multiple, their cost, operation cost will be high, manufacturing cost will be high, so they cannot sell their aeroplane. So with those 5, what they do, they have to prepare their plan such a way that one nacelle will go in immediately after 36 hours. There will be a person who will make sure that next oven is next nacelle is going inside, and it is manufactured and coming out. And the temperature, sometimes they deal 800 to 1200 degrees centigrade. They also deal with very high temperature. So this is the waste, I can say it's a wastage of time, where we are not utilizing all the resource properly. So industry thought we will not use composite. We have to come out this technology of the curing of the composite. So then this thermoplastic has come. It don't need any curing in the oven. It don't have any lean period. So what will happen with that? The production rate will increase. If we see the Airbus and that Boeing, mostly every 6 month or 3 month, we'll be reading a news that these many aircrafts are in the backlog, and they are in tremendous pressure to deliver more and more aircraft. And how can they speed up if their manufacturing is not speeding up? If no new technology is coming, so this is the answer for them. They got this will be help with the using thermoplastic. They'll be able to speed up their manufacturing, and they will be able to deliver more and more aircraft. A very good point is here, extremely good tensile and flexural strength with varying load. This is just a few lines, but it has very deep meaning in the aerospace industry. Extremely good in tensile. So just think for a pressure vessel, a cylindrical body. When you apply a hoop stress, what happens? What kind of stresses it develop? Mostly shear, tensile shear, and sometimes suppose it's enough length, some bending will happen. So that's what written here. The extremely good tensile and flexural. So most of the aircraft component, either fuselage or wing, they face shear and bending stresses. Mostly the shear stresses. And maximum are the tensile in the fuselage, and in the wing, compression too. So for the fuselage, it is very promising. For the nacelle, which is nacelle is a cowling of over the engine. This is also very promising here for the nacelle too. These two requirement, this thermoplastic requirement will help in the aerospace industry. The, this point I will highlight: excellent chemical resistance. Why it is important for the aerospace industry? Why we need a excellent chemical resistance component? So the basic behind this is aircraft operates in atmosphere, and it doesn't operate in the fixed environment. In day to day life, if we do any testing, we do in the room temperature. If a metallic allowable we have to generate, suppose given a aluminum sheet or composite sheet, and someone say that do the testing and develop the allowables for that, how much tensile strength is there, how much compressive strength is there, we'll be doing in the room testing. But aircraft will be flying far away, a different ambient conditions. Aircraft may go to Dubai in a very hot region. Aircraft can go to Same aircraft can go immediately to Russia in a very cold weather. It can come to USA. It can go to in the atmosphere where the sea region. So above 18 kilometer from here ground to 4 kilometer, 5 kilometer till 18 kilometer, atmosphere will be keep varying, and that also keep varying depend upon which country, region, zone we are operating, because the aircraft has to land there in that atmosphere. So atmosphere reduces the strength of the material. It reduces, degrade the properties of the composite and the metallic. So what happens? Some of you may be very familiar, and some of you might have read and are maybe reading in upcoming curriculum. Fatigue. We might have heard the body fatigue. So for the aircraft also, the fatigue is a very common load, which in day-to-day scenario when the aircraft operates. So that loads drastically decreases the aircraft properties, and the structure can collapse. Lot of the bridges collapse due to fatigue. In a very simple way, we can understand why we need overhauling of our car, or why we need overhauling of our two-wheeler bike, motorbike. When we are going road, hump may come, pits may come, straight road may come, any other hurdle may come, and we operate every day. When we operate, the fatigue is happening on those wheels, alloys, bodies. and the degradation is happening. That's why after a certain period, 3 month or 6 month, we go to a overall shop. We say, okay, please do the overhauling of my motorbike or car. Same way aircraft also needs, it is also operating in a fatigue environment conditions. So when that fatigue environment condition, my properties are degrading, I have to protect my property. Means if aircraft is flying today and if it is flying after 10 years, someone can say confidently, after 10 years also my aircraft is brand new. It means the life of the aircraft is more. In ideal situation, when the aircraft is losing its life in 25 years, when we are using this excellent chemical resistance material, so my life will be increasing. We can easily sterilize. Low smoke and gas emission happens when we use this excellent uh, hydrolysis resistance and resistance to energy rich radiation. So it radiation much happens in this thermoplastic. So it's a very good technology. The recent challenge from my industry experience I'm sharing, whatever the recent challenge I have seen in the thermoplastic, some of the double curvature and where the fittings happens, so two or three component come and join together, that location, because thermoplastic is basically the molding. And molding, what they do, they prepare a dia and they stretch from the side, and we have to know very precise location which are the point we have to stretch sometimes to bring it a proper shape. So that has not been evolved technology wise for generating a complex shape. So that we are working on, still industry is working on. And Airbus and uh, their target is by 2025 their manufacturing technology on the thermoplastic should be such that they can even develop and create a complex part. As of now, 50% of the aircraft parts are identified, which are simpler to convert into the thermoplastic. And a lot of investment is happening over the period. So suppose anyone can keep his aspiration upcoming days to work and know more in the manufacturing industry and how to upgrade that manufacturing industry, which can help to adopt the new kind of materials and provide solution to the industry. I will be moving to the next slide, which is MQ-25. This is a collaborative combat aircraft. So previous slide I have shown there was a need, and hence we come across and find out the solution. One was in the fuel, another was on the material. And this slide, the purpose of keeping this slide is aerodynamic. Not only fuel, not only the material, even the aerodynamic design can also help us to reduce the fuel. So this is stringery design. Stringery is a fish shape. Many of you might have seen that. From the nature we have adopted this design and they have created. It is a refueling door. USA government started pushing, US army, US aviation and seals, that why can't you adopt the product which are common. Maybe aircraft air force will say, I need a aeroplane, my in my aeroplane my component specification should be X, Y, and Z. Now, next time the Navy will come, they will say, in my product, my aeroplane for that cargo need, I need this product specification CDE. The US government say, why? Even other countries, industries are saying, why can't we collaborate? Why can't we make a common product? Why can't we define a standard specification which can be used across multiple domains? So what happened with this? When we optimize our specification and use in the multiple domains, multiple need, then we reduce our waste. We know what development in the technology or industry we have to do. So this is the MQ-25 development of this aircraft. Behind the reason of that was reduce the specification, don't demand. So for example, in a home, a four kids are there and every kid is demanding different food based on his interests. So a mother has to prepare four different food. But if all the four kids collaborate and if mother can convince that you all need the food which I am preparing for you, you should be thankful for that. So the need we have standardized, we have reduced. The same concept we are applying there. So when I say that stringery fish, which is used and has people has thought that this shape can be in the shape way. The motivation of keeping this slide and sharing this thought process is look your surrounding. There are many shapes designed which nature has given you already. Sit for 5 minutes and think that is this designed? What is created by the nature? Can I use somewhere in my real life creating a product, creating or make a easy solution for the life? So there is nothing. This is my personal belief. There is nothing. There is no design which does not exist in the nature. Means all the designs for our need, for the human need, is available in the nature. Only we have to think, understand, and utilize those design for human life. So it's a very robust autonomous refueling capabilities. It's a seamless career deck range integration. It with this design, they have extended that operational range. So CBARS system is there. It says carrier carrier based aerial refueling system. So that is used in this technology, and we can save this by using this advancement in the aerodynamic, improving the aerodynamic efficiency. With this technology, we are reducing the CO2. Jeto Terra. This is a company name basically. This is not a aircraft name, aircraft model. This is a company name. It is a propulsion system drone and the aerial mobility startup company. So just see the shape. You will see something different. How many of you able to think that where is my engine? Most of the time, you might have seen a traditional engine cylindrical shape, and there will be jet. Even the first year curriculum in the thermodynamics or the jet engine, you'll be seeing always axial flow compressor module, turbine compressor, then turbine. In between propulsion system, you will be reading, and you'll see no, where is the engine here? That technology is not there in this air design in this drone. So that's the innovation. This in this fluidic propulsion system, this is a coupled with uh, revolutionary. If you see that airframe, see the airframe design, very aerodynamic shape. If you see the nose to the windshield, go to the back, and just imagine if the flow is coming from the nose of the this design, and easily it will go and pass. It's very lightweight, no propeller, and when it flies 30 dB quieter compared to. So not only CO2 emission, even the noise reduction we have to do. that also is there in Paris Agreement. So this technology is serving that purpose. So in this, we will not see any visible moving part or the propeller. So what is used in this technology? So in this technology, use a relatively small flow of compressed air from a turbo compressor to suck in a much greater volume of ambient air, which creates a vortex that significantly amplifies the airflow and creates a aerodynamic movement. So that design saves the fuel, the need of the fuel. Now coming to the clean 3, continuous lower energy emission and noise. This is more towards the same as overall the global level we have to reduce that CO2. But in aerospace industry, a dedicated committee they have formed which works in this technology, the clean. The clean technology is clean one, three phase, clean one, clean two, clean three. And the objective is that quantitative goal for subsonic fuel burn, emission, and noise reduction under clean three. So what is in the clean one and clean two phase? Clean two phase is slightly delayed due to COVID. That R&D fund was not released for the many of the company. Safran is working for a propeller aircraft, Safran Aerospace, which is also known as Spirit Aerospace. Rolls-Royce is working. Collins Aerospace is working on this clean technology. Boeing has already adopted some of the things and they are working on a product called Eco Demonstrator. In this technology, 25 dB cumulative noise reduction we have to do. And by 2026, hopefully we will meet that or it may delay one more year by 2027 just because of COVID. But we are also planning that 33% reduction in the fuel and it is implemented phase by phase. So every 5 years, what NASA FAA is doing that. So last 5 years, what are the technology has happened and matured? They say it is approved from suppose 2018, a technology has been approved and matured. They're saying implement it immediately in coming 5 years, phase by phase, keep changing the aircraft parts, implement it. Overall objective is 2.6% reduction in the fuel burn by 2050. How much fuel saving will be doing? Will be doing 9.3 billion gallon fuel saving by adopting this procedure. And if I have to quantify how much is the 9.6 billion gallon, just a very rough number, I will say, almost you can say 700,000 to 800,000 cars will be removing between now to 2050. So that much fuel we can save. You can just imagine that. It's not a easy thing. It's a very big number. So I will share some more insight. So slide I will be sharing anytime you can read. But my objective is from my practical experience, I should share more and more what is happening in the industry. So what next coming students has to think where they have to think and what new technology they have to work to develop a roadmap for upcoming 50 years. In the clean one phase and clean two phase, you might have heard high bypass ratio engine. So in jet engines are there, propeller engines are there. What happens here? They are saying identify all those engines which can reduce noise level and emissions. And the one example is ultra high bypass ratio engine. So we you might have studied or you may be studying soon in the conventional jet aircraft when the air comes, this is called intake, inlet. We say inlet cowl. In the aerospace industry, we say inlet cowl. It's a very big uh, airflow has to come inside this duct. When the airflow will come, it will go pass through these fan blades. It will compress and go to that compressor. Then fuel will burn here in the engine and then go to turbine. Only the some air goes into that engine, but rest of the air bypasses from the top above the engine. You can see that brown color. You can see the gray color. Gray color shape is the engine, and between gray color shape to that top, you can see that blue color. In between, whatever the space you are seeing, a fan is big shape. There it goes the bypass airflow. And high, when the high bypass is happening, so what is the current trend ratio? Current trend ratio is 8 is to 1 bypass or 10 is to 1 bypass. So what is the limitation? If I increase the bypass, my engine will be more efficient. So why can't I increase simply my bypass? There is a limitation of the cowling and shape, and that structure has to how it has to fix with these engines. There is a limitation in the design. So industry has thought, let's come out. What we will do, will not be using any cowling. In the figure 1 left hand side, you will be seeing there is a cowling. But if you see the figure 2 in the Safran engine, you will not see any cowling. So what it is doing, there is a fan behind the engine. It will be rotating. It will suck the air from the atmosphere, and virtually it is understanding the atmosphere itself is a duct. So this technology is considering my atmosphere as a duct, and it will suck the air with a high flow rate, and it will improve the bypass. So there is the answer. So okay, I got the answer. I can improve my bypass considering the atmosphere. But this is not the only one solution. There are many other challenges happening which industry is dealing now. The major challenge in this ultra high bypass ratio engine is the location. Where to fit that? Air comes from wing leading edge and goes towards the wing trailing edge and go further aft to the fuselage body and that aircraft elevator and the aileron side. Conventional single aisle wide body commercial aircraft, which we are seeing in the day to day life or we are traveling, engine will be on the wings. If I have to use very high fan blade design, the fan blades, if you can see, very big, then I cannot keep this engine beneath the wings, because if the fan blade is high and if it rotates, there are chances the wing, it may go, the wing design may limit. If we keep sufficient forward from the wing, then there is a chances of instability of the fuselage. The pitch nose up and nose down moment may not be much controlled way. And to control that, we need further, we have to add weight at the after side to counterbalance that pitching moment of the aircraft. 737 Max incident, the aircraft crash, many of you have might have studied or read in the newspaper. So similar thing, it may happen that if we keep further aft or keep much away from the wing bottom, the design stability problem will come, aerodynamic stability problem will come in the design. Okay, so I understand there is a stability problem if we keep a big fan in near the plane. A person may suggest this picture shows good answer. I can keep it on the aft. Yeah, that is answer. But for the challenges happening from the wing, if we have a big aircraft, and from the wing, if it is a business jet aircraft, it is fine. If you see, this is kind of a small engine. It's not a very big engine. So if we have a using this technology on the business jet aircraft, this is fine. But a very big aircraft where the wing is very big, so flow coming from top, it generates the vortex. Maybe that vortex flow velocity, that velocity air will go to this engine, then I may not get from that efficient air in this direction where the blades are. So also I have to think the undisturbed flow has to come to this engine blade, and then only I will get best and high bypass efficiency. So as much as possible undisturbed. If we keep too aft also the engine, then again it may happen. The nose down pitching moment, or sorry, nose up pitching moment will happen. If suppose CG is at that fuselage and mid side, then we need some other mechanism to counterbalance that moment. So these issues will be keep coming. So these are the real industry challenge. If a student has to decide, okay, I have got so many industry challenge, so many problems. What should I do? So my suggestion will be for the current students, form a small group every week at least once. Debate what industry wants. Note down only 5 points. Only note down the 5 points. What industry wants? What are the challenges? And when you are studying your curriculum, whichever subject, whichever topic, again think back what is the industry challenge and how can I relate my this subject to the industry challenge. If I am studying in mechanical engineering, thermodynamics, relate it the industry problem, and convince yourself if you will study thermodynamics well, you when you become a good engineer, you are going to solve an industry problem. You're not studying thermodynamics to become a graduate engineer. You are studying thermodynamics to solve a real industry problem in the future, and you are going to set a trend what upcoming engineers in 2050 will be doing. If you are studying fluid dynamics, or if you are studying the aerodynamics, you know the industry challenge. When you study, think, ask the questions. You ask questions your professors, mentors. With this study, am I able to solve this industry problem? If not, so ask the gap. What can I do to fill this gap so that when I'm an engineer, I can solve that problem? If you're studying electrical and electrical knowledge, ask the questions. How can I become a good engineer for the battery technology? What new innovation I can bring which can solve either in the car or bike or in the aerospace aviation industry or any other manufacturing industry. When you are studying laboratory, going to laboratory, solving one problem, then ask how we do test, how we develop this material allowables. And if your curriculum is not there, then this is the right time. Form a group, a small group, 4 student, 5 student. Search the answer. whatever the knowledge available in the open sources or with the industry expert. Connect with them, ask the questions, all defined questions, which helps you to gain your goal. So that is my key message to every of you students. I wish you all best of luck with this. I will close my session. I think uh, I'm just took all my time. So objective of this presentation is, and the sharing the industry knowledge is, do not study just to pass. Ask the right questions. Many times it may happen that you may not your answer directly in your organization. There are ample of sources in open forum and industry experts. Connect with them and keep learning. And same time, it's not only you'll be learning. Same time, with those industry people, from your question, sometimes they also get ideas. They also learn from you. It's a both way. I have also, someone has asked the questions, then I learned something from his question because I was trying to find out the answer. While finding the answer, I learned and then I implemented in my work. Now this is the open forum. So it's a question answer session. I can take some of the questions, if any.
Thank you,
Hope
Mr.
you all
Pandey. Yeah.
hope you all have enjoyed my session, and I was not boring, obviously.
Thank you, Mr. Pandey, for your valuable insights on upcoming trends on aviation industry. So no, now the forum is open for the questions. Any questions from any questions about aviation industry, how to get in or something, whatever you want.
Or in front, other than questions, if you have any thought, means uh, you can share with me, and you can ask that this is my thinking. There is no thinking right or wrong. Your thinking is always welcome, and I can share my view on your thinking.
Anyone? So, Mr. Pandey, I have one question. Like, they are from different backgrounds rather than aeronautical engineering. So,
Mhm.
how the other disciplines can be get into the aerospace companies?
Yeah, this is very good question. So aviation industry is not only that mechanical engineering. If you see, we do avionics, which is electrical engineering. We do that software development, which controls that how the flight operation will be happening. So electrical, electronics, and the software industries uh, can anytime they can come to aviation industry because we need a lot of software development. A passenger has to board in the flight, ticketing industries, and huge number of data is there. Huge number of knowledge base has been done on the paper, which we have to convert into the digital form. And tracking every flight from is very tough. We are doing a lot of R&D. We are not able to maintain record of all the R&D. So without a software developer, industry is also moving a fast phase. Without a need of software developer, we cannot meet our schedule and deadline, because a software developer helps to develop various engineering tools for us, which we use in our day to day life, and then we solve a mechanical problem. A software developer and a electrical engineers designs all the routing, wiring, and how electrical control system will function. Same time, if you see recent industry, either NASA or India, ISRO, Indian Space Research Organization, NASA Research Organization. We need more person who has good knowledge in the computer science and good knowledge in the physics. They don't even means engineers are required. Even those who are good in the physics, those who are good in chemical are required. The chemical industry engineers required for the battery technology, they can develop a good chemical solution. They can come up a battery which can be charged faster, and its life will be more, and it can generate more power, which degrades in the environment very less. So that will be helpful. This way, aerospace industry covers almost all the domain. I myself has interviewed and had some of the electrical engineers, some of the mechanical engineers, and some of the computer science engineers for our need in the Boeing.
Thank you, Mr.
Hope I
Pandey.
have answered.
Yeah, you answered. So, anyone else? So, I think it's an end to this session. So, thank you, Mr. Pandey, for joining us.
Thank you, Dr. Brijesh, and thank you, Felix. Thank you, Professor Potingling, and thank you, university, and thank you all the university staff. I'm also very thankful to all the students, um, and it's my pleasure to give my online lecture here. Thank you all. Have a
Thank you,
good
Pandey.
day.
Thank
Bye.
you. Bye. So, this was now the only there is one more lecture for your course. Then there will be a presentation, final presentation on 15th. So you have to be ready for the final presentation. Those comments which have been on the first presentation, you incorporate that comments and complete your work. Is it okay? Any questions about your final presentations? Yeah. Now you have to complete it. What you have proposed it. That was a proposal. Now you have to do some work on that. That was your proposal. This was your work completion. So you get the 15 days to work something on that. Maybe you propose something. You present some designs on after your proposal completion. That was proposal evaluation, and this is the work completion.
They can speak over time.
Uh,
Okay, maybe 7 to 8 minutes. That's
and this time prescribe on your the time limits. Last time some have taken 15 minutes or 15 minutes. Be precise on the time limits, because this evaluation score will be add to your score. So gather all your teammates. You have a 15 days. That's why we talk about the final presentation today. So you had one more lecture and then you have the final presentation. Any question about that presentation or something or more? No? Thank you very much for today's session.